Hello once again, physics students at North Tahoe High. We're going to watch this quick video lesson, and we're going to hopefully learn the basics of charge, electric force, and the electric field, so we may work together in class to learn more about it and go more in detail. The subjects I want to address and the things I'd like you to come away with this are: 1, how do objects gain charges? Pretty basic. Number 2, how do we calculate the force between charged particles? Some math there. 3, what is the electric field and how do charges respond when placed in an external electric field? So a really abstract but not too difficult mathematical idea there. And how do we calculate the electric field strength? So let's begin. How do we charge an object? I'm going to tell you a joke, and if you get the joke, not only are you a proud physics and chemistry nerd, you really understand the basics of how something acquires a charge in the first place. Adam walks into the bar. It's kind of depressed and down and glum, and the bartender says, "What's wrong, Adam? You don't look like your normal self today." Adam responds, "I think I lost an electron." And the bartender says, "Oh no, are you sure?" And Adam says, "I'm positive." Oh, I'm here all week, folks. You can back that up and listen to it over and over again. But anyways, as silly as that joke is, it really does have the basics of it. If an object loses electrons, it becomes positively charged. Because all objects are made of atoms, and all atoms start off, you can think of neutral. That means they have the same number of protons as electrons. If you lose some negative part of you, you are left with more positive than negative, so it's positively charged if you lose electrons. If an object gains electrons, it becomes negatively charged. So in chemistry, we studied a lot of the consequence of these charging things, but we didn't really look at the physics of how or why it works. Let's just take a look at the formation of salt. Sodium starts off neutral, and if you remember, sodium has that one valence electron which it easily gets rid of. Chlorine starts out also neutral, but chlorine has a spot in its valence, a shell, to fill it, to get that full 8. So that's exactly what happens in nature. Sodium loses an electron and becomes positively charged. Chlorine gains the electron. Now it has one more electron than proton and is negatively charged. These two things have opposite charges, so they are attracted to one another. And that's the physics of what makes salts, or all ionic compounds for that matter, come together, the attractive electrostatic force. So of course in physics we want to be able to calculate how strong in magnitude are things attracted to each other because of their forces. The name to this law, the name of the equation you're going to see, is Coulomb's law. Let's start off with some basics that you already know going into this, hopefully. Remember, we talked about like charges, whether they're two positives or two negatives, they repel, and opposite charges, they attract. So what we're going to actually look at is how do we calculate the force of attraction or the force of repulsion. So we're going to go ahead and call this the electric force, so F sub E. And we're going to find that there's a constant involved, a constant of proportionality, which is K. Sometimes it's called the electrostatic constant, sometimes it's called Coulomb's constant, but here is the value. We can usually get away with just rounding that to 9. 9 times 10 to the 9. 9 billion units, Newton meters squared per Coulomb squared. So what else is going to determine the strength of attraction or repulsion is going to be the actual amount of charge that we're dealing with. And in physics, we use Q, small variable q, for charge. One charge does not a force make. It takes two to tango. So we have two charges here in that case. So Q1 and Q2. Q is the variable for charge. And charge is measured in something new to us in coulombs. So the unit for charge will be a capital C. And we'll put this together towards the end. So what does that mean? It means if I have two charges, so here's two positive charges, that the strength, in this case, since they're both positive, that they repel each other with, is a product of the magnitude of the charge. So how could I make them repel each other more? I could just give one more charge. So in this case, this one right here has 3 times the charge as this one. So the amount or the magnitude of the charge is directly proportional to the force between them. It should be noted, right, that they exert equal and opposite forces on one another. There's two charges produce one force, but that force is the force that's on each individual charges, and I'll try to trick you on the next slide with that. The other factor that influences the strength of repulsion or attraction between charges we may have read about is the distance between them. And sometimes books use D for distance. Our books usually use R for a radial distance between them. It's another example of an inverse square law, so that's a really important idea. And what it says is this. If I have a charge, two charges that are about 4 centimeters apart according to this ruler, and I double the distance, so I take them from 4 to 8, well, we've already learned from our reading that the force of repulsion between them will lessen. It'll get weaker because they're further apart. But I've doubled the distance. That doesn't mean that it gets weaker by a factor of 2 or it's half the force. This inverse square means that we've dropped the force by a factor of 4, 2 times R. We'd square that and we'd have a 1/4 factor. So the force would be reduced by a factor of 4. It's an inverse square law, and we're going to practice more things with that. And we've seen an equation that looks exactly like this, almost, in terms of its form, with universal gravitation. Remember, universal gravitation looked like this. The force between two masses, the attractive force, was a product of their masses and the distance between them squared. We also had that constant of proportionality. The big difference, G, is on the order of the magnitude of 10 to the negative 11. Our constant is 10 to the positive 9, so 20 orders of magnitude difference between these. This is why we say relative to most forces, the other forces, gravity is so incredibly weak. So here's that trick I promised you. Charges 1 and 2 exert repulsive forces on each other, right? They're both positively charged. The large charge is 5 times greater than the small charge. Which statement would be true? Would it be correct to say that the force on, and this will be object 2 rather, this is object 1. Whoops, scratch that, made a mistake. Object 2 is 5 times greater than, the charge is 5 times greater than the charge on object 1. That's what this says. So what would we say? Would we say the force of 1 on 2 is greater than the force of 2 on 1? Would we say the force of, or that's reversed, the force of 1 on 2 is less? The answer is this one. So this is sort of like that problem we talked about, we tried to wrap our minds around with gravity. This is an action-reaction pair here. They cannot push each other with different amounts of force. Just like it's strange to say that the earth pulls me down with as much force as I pull the earth up. That's exactly what we're saying here. Charge 1 pushes charge 2 with this force. The equal or the action and reaction pair to that would be that charge 2 pushes charge 1 with that force. Coulomb's law would calculate then the magnitude or the strength that that push occurs with. All right, so lastly, the highly abstract and conceptual idea of the electric field. A lot of things in nature produce field. We might be familiar with the gravitational field. We didn't need the idea of the field really to study gravity at beginning physics. We do really need it for electricity and magnetism. So let's talk a little bit about what a field is. Every charge alters the space around it, producing an electric field. So just by virtue of having something that's charged, an excess or a deficit of electrons, it produces an electric field. The bigger the charge, the stronger the field it produces. Similar to the big planet produces a greater gravitational field. Other charges located in the field experience a force from the field. So if you hold me up above the Earth in the Earth's gravitational field and you drop me, I fall, I accelerate. There's a force on me because of that field. The same thing is true of charges in an electric field. The field strength describes the force on a charge at a location in that field, and the unit of electric field strength is newtons per coulomb, or N over C. Let's talk a little bit about what the field is trying to tell us. So what we see here is a large charge here, and by size it is, but really what we should mean is it's got a lot of charge inside of it. So this is our large charge that's altering space. It's producing an electric field. We're going to imagine the concept of what's called a test charge or a probe charge. And that would be this little guy right here. He's so little that he does have an electric field, but it's so small that it doesn't really affect the interaction between these two. Just like I'm so small that my gravitational field doesn't really affect the behavior of the Earth's gravitational field. Although technically I do produce a gravitational field. So this object, our large object, produces a gravitation, or produces an electric field. It alters the space around it. And if I bring charges in that space, in that altered area, which we call the electric field, it exerts a force on this charge. So how do we calculate the strength of the field, or the ability of the field to exert a force on a charge? Would look like this. So let's look at Coulomb's law here. It says that the force between them is the product, as related to the product of the charges, and inversely related to the distance between them. And let's call the big charge, the one that's significantly altering space, let's call the big charge Q1 here. And the little test charge, that's field is so small it doesn't really come into play in the problem. We're going to call Q2. So if we want to know the force that's on this little Q2, this test charge, what we're really after is the force, the newtons of force per coulomb of charge. So essentially what we do is we take the force, Coulomb's law, and we divide it by the magnitude of the charge that we're putting in the field. Remember, Q1 produces the field, we're putting Q2 in there as a test charge, so we're going to divide it by Q2. And this is the relationship we get. We'll find out that that Q2 cancels in this case. So this is the equation for the strength of the electric field produced by the big charge Q1 at any region in space, distance r away from the charge. So cleaned up a little bit, here's our expression. What this means is Q, big charge Q here, produces an electric field, and its electric field has a known value anywhere in space near it, whether or not there's a charge there, another charge there, or not. So at point 1, I could calculate the electric field produced by charge big Q, and the field would point in that direction. So the field is a vector. So that means if I did bring a charge and I put it at that location, I could easily calculate the force that that charge would experience because of the electric field at that location. Also, we know that the electric field, just like the force, varies with distance. So if I double that distance, I expect the value of the electric field strength to go down by a factor of 4 because of that inverse square law. So again, the electric field will exist in this point of space whether or not I put a charge there or not. But if I put a charge at that location, the electric field is going to allow me to calculate the force on that charge because of the field produced by this big guy. Complicated idea, abstract idea anyways, and we're going to practice this though, so this is only the first time through. Okay, so go ahead and fill out the Google form for your homework credit, and we will discuss and practice together tomorrow.